They shouldn't try, yes. কি হবে? তুমি কোশ্চেন দিছো।
ফার্স্ট কোশ্চেন কিছু হবে না
খুলে দিচ্ছি।
নো প্রবলেম।
বই চ্যাপ্টারটা খুলে দিই। চ্যাপ্টারটা না পুরো ইতিহাস। কি শুনছিস?
The first question, out of these you have to write any five.
Okay. Five মানে কি করে
Like clothes is 1, paper is 2, fuels is 3, medicines is 4, rubber is 5, plastic is 6, soap is 7, detergents is 8. You have to write any.
Any five words.
Okay, good evening all of you. Today we are going to start, we are going to do a chapter called Radioactivity. Now, what is the basic concept behind radioactivity? Why does radioactivity happen? As you know that radioactivity is a nuclear phenomenon. Radioactivity doesn't happen in the entire atom, it is specific only to the nucleus. What happens is that in the nucleus of any atom, you have neutrons and protons. And if the number of neutrons is n and if the number of protons is z, then there are certain nuclei which are stable. That means they will not disintegrate. What is radioactivity actually? Radioactivity is nuclear disintegration. So when the nucleus disintegrates, that phenomenon is called radioactivity. So there are basically two kinds of nuclei which are stable. You can have light stable nuclei, you can have heavy stable nuclei. So these are the two types of nuclei which are stable. Okay, you can have light stable nuclei, you can have heavy stable nuclei. So in case of light stable nuclei, what happens is the number of neutrons divided by the number of protons is almost equal to 1. So if you say that the nucleus is a light stable nucleus, the number of neutrons by number of protons is almost equal to 1. If you say that it is a heavy stable nucleus, then the number of neutrons by number of protons is approximately equal to 1.6, right? Now this was an empirical study, or rather experimental study. There isn't any basis for this, like there is no mathematical basis for this. This was just studied and investigated by experiment, that on one hand you have nuclei which are extremely light, hydrogen, deuterium, etc., and they have stability, they don't necessarily have stability, but I'm saying very light nuclei will have stability if number of neutrons to number of protons is almost equal to 1. And if it is a heavy nucleus, then number of neutrons to number of protons approximately equal to 1.6 for stable nuclei. Now suppose there is a light nucleus and number of neutrons to number of protons is not equal to 1, it is something different. Like suppose n by z is not 1, it is some other value, it is something different from 1. So if n by z is something different from 1, then what will happen? The nucleus will disintegrate, and the disintegration will be in such a way that the n by z becomes equal to 1. Similarly, if you have a heavy nucleus in which n by z is not in the range of 1.6, then the nucleus will disintegrate so that the n by z value comes in the range of 1.6. So the point is that radioactivity essentially is the disintegration of the nucleus. Now when we say disintegration of the nucleus, what does it mean? It means that the nucleus will change its character. And you understand that the nucleus is what defines the atom. You define an atom by its nucleus, because the outer electrons, they can always undergo a transaction and whenever a chemical reaction is happening. But the character of an atom is defined by the nucleus. So if the nucleus has a change of character, that means the whole atom has a change of character. So whenever there is a light stable nucleus, the number of neutrons to number of protons, if it is not in this range, then there could be a change from neutron to proton, like neutron may convert to proton, or the vice versa may also happen, proton may convert to neutron, and that conversion will ensure that this ratio is in a stable range. Similarly, in case of a heavy nucleus, if the number of neutrons to number of protons is not in the range of 1.6, there could be a conversion of neutron to proton or proton to neutron, so that this ratio comes in the range of 1.6. So radioactivity is the phenomenon by which the number of neutrons or the number of protons in the nucleus undergoes a change, right? Well, to be honest, if one undergoes a change, the other will, because see, if neutron changes to proton, then number of neutrons will decrease, number of protons will increase. So you may say that the thing which has undergone the change is neutron, you may say that. But the number of protons will also get affected because of that. So radioactivity is a phenomenon by which the number of neutrons and the number of protons in the nucleus, the quantity of neutrons and quantity of protons is affected. And after the nuclear transformation, the quantity becomes some other quantity, and that new quantity will automatically mean that you have got a new nucleus, which would automatically mean that you no longer have the atom with which you started, now you have a new atom, right? So that is the concept of radioactivity. Okay, now Okay. Uh, First thing we need to do is that we need to get an idea about the size of the nucleus. Actually, the size of any nucleus is given by the formula R equal to R0 into cube root of A. This is a formula which tells us about the size of the nucleus. So R is the nuclear radius. R0 is a constant value, 1.1 10 to the power minus 15 meter. By the way, 10 to the power minus 15 meter is called femtometer. FEMTO, femtometer. So R0 will be 1.1 femtometer. So R equal to R0 capital A to the power 1/3 and R0 is 1.1 femtometer. Now capital A is the mass number, volume is 4/3 pi R cube, and instead of R you can write R0 A to the power 1/3. So 4/3 pi R0 cube into A. So this is the volume. So density is equal to mass by volume, and you know that the mass of a nucleus will be proportional to the mass number. So mass by volume, so A by V, so 3 by 4 pi R0 cube, and 3 by 4 pi R0 cube is a constant because 3 is a constant, 4 pi is a constant, R0 I have already told you is a constant. So that means nuclear density is a constant. So once again, the size of any nucleus is given by this formula. So the size depends on the mass number. A is the mass number. But yeah, and the volume of course will also depend on the mass number thanks to the fact that the radius depends on mass number. But the nuclear density will be constant. It will not depend on the mass number. Okay. Now, the thing is that when you are dealing with subatomic particles, there is a concept called mass defect. Mass defect is a concept which applies only to subatomic particles. Just excuse me.
Oh.
So, So basically, when you discuss about subatomic particles, then there is a concept called mass defect. Mass defect means that when you have subatomic particles coming together, then after they come together, the mass of each of them individually will not add up to give the mass that you will get when they are together as a whole. So there will be a difference in mass, and that is known as mass defect. So binding energy of a nucleus, what do we do for this? You first find out the total mass of all the protons. Okay, whatever protons are there, you find the total mass of all the protons. So total mass of the protons is atomic number into mass of protons. then you find out the total mass of all the neutrons. So whatever is the number of neutrons into the total mass of all the neutrons minus the mass of the nucleus itself. That means, like I said, you have neutrons, you have protons. So individually the total mass of all the protons, individually the total mass of all the neutrons, and then the mass of the nucleus itself. You will find that the total of these two will be more than the mass of the nucleus. So this is called mass defect. Mass defect is something which is unique to subatomic particles. Obviously in day-to-day life we cannot even comprehend something like mass defect can happen, because in fact in as far as microscopic objects are concerned, we believe that mass is conserved. So the mass of the protons plus mass of the neutrons minus the mass of the nucleus, that is called mass defect. According to Einstein's equation, mass defect into c square is energy, and that energy is called binding energy of the nucleus. So what exactly does binding energy of the nucleus mean? Binding energy of the nucleus, as the name suggests, it is the energy which holds the nucleons together. So neutrons plus protons is equal to nucleons. Okay, so neutrons plus protons is equal to nucleons. So these neutrons and protons, they are being held together in the nucleus by, and that force which holds them together, that is called the binding energy of the nucleus. So it is total mass of proton plus total mass of neutron minus mass of the nucleus into c square, right? So how do we define binding energy? So we say like this, that okay, so binding energy of nucleus. Okay, so neutrons and protons together, they are called nucleons. The total mass of protons plus total mass of neutrons minus the mass of the nucleus into c square is called binding energy of the nucleus. So what is binding energy of the nucleus? I have already told you, it is the energy which it is indicative of the energy that holds the protons and neutrons together to form the nucleus. So you can either say that binding energy is the energy required to separate the nucleons to infinity. You can say that. That is, the nucleons were there inside the nucleus and now you have to separate them to infinity. You can say that, or you can say it is the energy released when nucleons come together to form the nucleus. So these are the two ways in which you can define binding energy. Either you can say it's the energy required to separate the nucleons to infinity, or it is the energy released when nucleons come together to form the nucleus. So these are the two definitions of binding energy, right? Okay, now what is the significance of binding energy? See, if the binding energy is high, that means that the nucleus is expected to be very stable. If the binding energy is low, that means most likely it will not be a very stable nucleus. But what the scientists actually discovered was that the binding energy itself doesn't give a very good idea. The average binding energy per nucleon, it gives an excellent idea about the stability of the nucleus. And how does it do that? Let's have a look. Okay, so I was telling all of you that the binding energy, uh, the binding energy depends on so the thing is that let us do one thing. Let's now understand graphically what this topic is all about, binding energy per nucleon. So I have drawn a graph. In this graph, the x-axis is mass number. Okay. So in the x-axis of the graph, you have mass number, and in the y-axis, you have binding energy per nucleon. Okay. The x-axis of the graph has mass number, and the y-axis has binding energy per nucleon. So the x-axis is mass number and the y-axis is binding energy per nucleon. So basically what happens is that if you look at three elements, deuterium is the heavy isotope of hydrogen, then iron, and then uranium. Now for deuterium, the binding energy per nucleon is 2. By the way, the unit is mega electron volt. So the binding energy for deuterium, the binding energy per nucleon is 2 mega electron volt, and that is really low. That is really low. And for iron, the mass number of iron is 56. The binding energy per nucleon is 8.7. For uranium, the mass number is 238, and binding energy per nucleon is 7.5. So for deuterium it is 2, for iron it is 56, and for uranium it is 238. So the graph is increasing and then again the graph is decreasing. So that means that the binding energy per nucleon is highest for iron, and the binding energy per nucleon is pretty low for deuterium. So you can expect some radioactivity from deuterium. And again, when you go really high, like uranium 238, again the binding energy goes down. So the binding energy is very high for iron, so it is stable. It is extremely low for deuterium, so it can be radioactive. And from iron, as you go to uranium, it again goes down. So you can expect radioactivity from uranium. Which is why you will remember that when we started the session, the first topic was that nuclei, whether they are light or heavy, because radioactivity is found in extremes. Either it is light or heavy, right? So basically, the fact that iron appears to be very stable, that actually it was investigated and found the fact that iron is the most stable. So it was investigated and found that those who have mass number between 50 to 80, they are the most stable, right? So iron is 56. So those which are in the region 50 to 80, they have the maximum stability. So mass number 50 to 80 is the most stable. So this graph, it now gives us a very clear picture of what we started with, that ultimately it is the number of neutrons to number of protons, that ratio which needs a correction, and that is why radioactivity happens. But now we have an even better picture with this graph. We know that those who are in the region 50 to 80 mass number, their binding energy per nucleon is pretty high, so they are stable. Those who are much lower and much higher, they are the ones which you can expect will show some radioactivity, right? Okay, so that brings us to the first kind of radioactive decay. So we have understood now that those nuclei which are unstable, they will undergo radioactive disintegration. So radioactive disintegration is essentially of three types. We'll just have a look at all three of them one by one. The first one is called alpha decay, right? In alpha decay, what happens? This is the starting nucleus. We call it the parent nucleus, that is X. So mass number is A, atomic number is Z. Now this nucleus will emit a alpha particle. What is alpha particle? Alpha particle is a helium nucleus in which both the electrons have been removed. So after removing of both the electrons, you will be left with He42. And whatever else is there, that is called Y. So after you, from X, after you remove He42, whatever is left, that is Y. And the fact that you have got an alpha particle out of the nucleus, that means the mass number has gone down by 4, means it was A, now it has become A minus 4. And the atomic number has gone down by 2, that means it was Z, now it has become Z minus 2. So the mass number has gone down from A to A minus 4, atomic number has gone down from Z to Z minus 2. Just to give you an example, suppose X is bismuth, so bismuth is 212 and 83, and Y is thallium, so thallium is 208 and 81. So you started with the nucleus of bismuth and got the nucleus of thallium, and you have got alpha particle. So that means what? That you started with X and you got Y and alpha particle. So the total mass of X minus the total mass of alpha particle and Y, the difference of this is the mass defect. I told you in subatomic particles there will be a mass defect. So if an alpha particle comes out of the nucleus, just because the alpha particle has come out, that doesn't mean that the mass of the nucleus before the alpha particle came out will be equal to the mass of the nucleus after it came out plus alpha particle. It will not happen like that. There will be a loss of mass. There will always be a mass defect. In every nuclear transformation, there will be a mass defect. So the mass of X minus the mass of Y plus mass of alpha particle, this whole thing into C square, is called the Q value of the reaction. Now this Q value of the reaction, it becomes available as the energy of the products of the reaction. So the products of the reaction are capital Y and alpha particle. So Q value becomes the energy of capital Y and the alpha particle, right? Now Now what happens is that generally the Q value, it is found to be the kinetic energy of the alpha particle. So if you are wondering how is this Q value manifested, okay fine, there has been a mass defect, understood, there has been a mass defect, but that mass defect has corresponded to some energy. So mass defect into C square is the energy. So how is that energy manifested? So this energy was found to be the kinetic energy of the alpha particle. So the alpha particles which will come out of this decay process, they will all have a combined kinetic energy which is given by the Q value of the reaction. So this is the first kind of radioactive decay, that is called alpha decay. Then you have beta decay. Okay, so in this beta decay, the parent nucleus is X. So X will disintegrate to give Y, and when that happens, a fast moving electron will come out of the nucleus. That fast moving electron is called a beta particle. I have deliberately put a minus here because beta particle beta particle is an electron. It has same charge as electron. That's why I put a minus. And another particle comes out that is called the anti-neutrino. So this is the symbol of anti-neutrino. It is a chargeless, massless entity. So such entities can come out during nuclear disintegration. So you will observe that the mass number of the parent and daughter nucleus is the same, but atomic number has increased by 1. That clearly shows that a neutron has converted into a proton, because the mass number has increased by 1. Excuse me, the atomic number has increased by 1, but mass number is same. That means a neutron is converted to proton. That means, excuse me, Alok. Allotropy is the phenomenon by which various physical forms of an element can exist. Allotropy is the phenomenon by which various physical forms of an element can exist. So ultimately, what is happening, that a neutron is converting into a proton due to beta decay. Ultimately, a neutron is converting into a proton, and it is releasing beta particle and it is releasing anti-neutrino. So that is the important thing about a beta decay. Neutron is converting to proton, releasing an electron and releasing an anti-neutrino. Okay, now the thing is that the mass of X minus the mass of Y, so beta particle is an electron, so the mass will be very small compared to this nucleus or this nucleus. Antineutrino is a massless entity. So the mass of X will be obviously more than the mass of Y. By now we know about the mass defect thing. So mass of X minus mass of Y into C square will be the Q value of this reaction. The Q value of this reaction will entirely go into the energy of the beta particle and the antineutrino. So unlike alpha decay, in beta decay the Q value is consumed by the beta particle and antineutrino both. That means they both share the Q value as the kinetic energy, right? So whatever is the Q value is shared by both of them as their kinetic energy. So that is the difference between Q value of alpha decay and beta decay. Now beta decay, we saw that essentially it is a conversion of neutron to proton, but it can also be conversion of proton to neutron. Okay, next we have beta plus decay. In beta plus decay, what is happening is that this is X, the parent nucleus is X. So here the proton is getting converted to neutron, and instead of releasing a fast moving electron, it is releasing the positive equivalent of an electron, that is called positron. Positron has the same charge as electron, but it is positive and it is identical to electron. So that's why I have written beta plus. And instead of anti-neutrino, you get neutrino. And the daughter nucleus, the mass number, atomic number goes down by 1. So it's very clear that number of proton has gone down and number of neutron has gone up. And the Q value is equal to the mass of X minus the mass of Y into C square. And as you would expect, this Q value is equally shared by the positron and the neutrino. Not equally shared, it is shared between them, not equally shared. Now there is a very interesting concept called antiparticle. In case of subatomic particles, you have something called antiparticle. Antiparticle is a pair of particles which, if they annihilate each other, then their masses will be destroyed and completely converted to energy. So a beta particle and a positron, they are antiparticle of each other. That means these two, if they interact with each other, like if they have a collision, then they will annihilate each other and completely the mass will be destroyed and converted to energy. Similarly, antineutrino and neutrino, they are antiparticle of each other. They will annihilate each other in case of a collision, and the entire neutrino-antino combination will be converted to energy. So remember, beta minus and beta plus, that means electron and positron are antiparticle. Antineutrino and neutrino are antiparticle. And beta minus decay is conversion of neutron to proton, and beta plus decay is conversion of proton to neutron, right? Now, it was discovered by scientists that whenever any radioactive decay happens, whether it is alpha decay, whether it is beta decay, so whenever any radioactive decay happens, the nucleus which is formed, the daughter nucleus which is formed, like this is called the parent nucleus, this is the daughter nucleus, this is the parent nucleus, this is the daughter nucleus. So the daughter nucleus which is formed, it is formed in an excited state, right? Excited state means it is very unstable. So when the daughter nucleus is formed, it is in an excited state, it is unstable, and as a result of that, it tries to lower its energy to achieve stability. So something like in Bohr's atomic model, when an electron becomes excited, it tries to undergo a transition to a lower state to become stable, and it releases energy through electromagnetic radiations. So similarly, when a particle is undergoing a transition to a lower state, when the daughter nucleus is obtained during radioactive decay, it is obtained in an excited state. So it tries to lower its energy and become stable. So it lowers its energy by giving out gamma radiations. So that means what happens is that this reaction, the daughter nucleus is Y, so when it is formed, it is excited state, and it gives out gamma rays. Okay, it gives out gamma rays and becomes stable. So in any radioactive decay, the daughter nucleus is not formed immediately in a stable condition. It is initially formed in an excited state. It gives out gamma rays and then becomes stable after giving out gamma rays. Now these gamma rays, they are, as you know very well, they don't have any mass. They are actually photons, gamma ray photons. And whatever is the difference of energy between the excited state and the ground state, you might say, of the daughter nucleus, that difference of energy is supposed capital E. The difference of energy between the excited state of the daughter nucleus and the ground state is supposed capital E. So Hc by capital E will be the wavelength of the gamma ray photons. So this is the third kind of nuclear radiation, that is gamma rays. So how many nuclear radiations did we see? Alpha rays, beta rays and gamma rays, right? So these are the three types. Okay, now what we will do is we will study the law of radioactive decay. Actually, radioactive decay follows first order kinetics. First order kinetics you have studied in chemistry. Radioactive decay follows that. So we'll just have a look at that now.
Biggest break.
Okay. There is a very important law, the law of radioactive decay. Basically, the law of radioactive decay is just another version of first order chemical kinetics. So, in a radioactive sample, suppose let us say at any point of time, the number of active nuclei, that means the number of nuclei which are actually present, is capital N. So, capital N is the number of active nuclei. So the number of nuclei which will disintegrate further in time dt. So the number of active nuclei is n, and from the moment of time that we are considering, after another time dt, the number of nuclei that will disintegrate is dn. So according to the law of radioactive decay, dn will be minus lambda into n into dt. The reason why we have put a minus is because the number of nuclei is going down. So the number of nuclei at the start was capital N. Start means at any particular point of time it was capital N. From there, after a time dt, it has gone down by dn. So dn is minus lambda n dt. Now if you do dn by n, so that is going to be minus lambda dt. So suppose the initial number of active nuclei is n0, finally it is n. So initial time is 0, final time is t. So this one will be ln n by n0, and this is minus lambda t. So n will be n0 e to the power minus lambda t. So this will be the formula which will help us to find the number of active nuclei at any point of time t. This formula. And n0 is the initial number of active nuclei. Now, in the law of radioactive decay, if we bring dt to the left, then and with the minus sign, then minus dn by dt is number of disintegrations per second. That is called the activity of the sample. Usually we give a symbol capital A. Okay, so minus dn by dt is called activity. It means number of disintegrations per second. So if you write minus dn by dt is capital A, then in that case this reaction will become A equal to lambda n, and if you combine these two, then you can say that A equal to A0 e to the power minus lambda t. So this will be the equation instead of this, A equal to A0 e to the power minus lambda t. Now in this equation, if you put n equal to n0 by 2, so that means we are now wanting to find at what time the number of active nuclei will become half of the original. So in this formula, if you put replace n with n0 by 2, then n0 by 2 is n0 e to the power minus lambda t. So we will get time after taking log on both sides. We will get time is ln2 by lambda. ln2 is 0.693. So the half-life of a radioactive sample is 0.693 by lambda, right? So this is the formula to find the half-life of a radioactive sample, 0.693 by lambda. Okay. Now the thing is that, so half-life literally means what? It means the time after which the number of active nuclei becomes half of the original. So what we can do is that these two formulas, n equal to n0 e to the power minus lambda t and a equal to a0 e to the power minus lambda t, these two formulas, if we replace lambda with ln2 by half-life, so you will get n equal to n0 by 2 to the power t by half-life. Similarly, you will get a equal to a0 2 to the power t by half-life. So you could say that this is the law, but the useful ones are this, then half-life, okay, and in some cases these are also useful. The law is this, but normally we don't use the law for doing any sum, because the law itself is the beginning of some derivations, and those derivations are more important while doing the sums, like this one, and these two. Now suppose you want to find the average life of the sample, not the half-life. So for average life, what you have to do, you have to say like this, that suppose, let us say that at a particular point of time t, the number of active nuclei is n, right? So in a further time dt, the number of nuclei which got decayed was lambda n dt, right? So those nuclei which has got decayed in a further time dt, that means those nuclei have a life of t, correct? Because at a time t, the number of nuclei was n, and then the number of nuclei which decayed was dn is lambda n dt. So that means at a particular time, the number of nuclei which has decayed is lambda n dt, and this lambda n dt, if you multiply that with time, then that will be the total life of those nuclei. So lambda n dt into time will be the total life of those nuclei, and you have to integrate this from 0 to infinity to get the life of every kind of nucleus, right, from start to finish. If you want to integrate this, you will have to first replace n with n0 e to the power minus lambda t. Then you will get one integration by parts which I have skipped. Integration t e to the power minus lambda t 0 to infinity is integration by parts, so that I have skipped. So you will finally get n0 by lambda. So average life, so the sum of all the lives is n0 by lambda. So average life means mean life is the sum of all the lives divided by the number of nuclei. So average life is 1 by lambda. So these are the two types of lives that are important: half life ln2 by lambda and average life 1 by lambda. Another thing that is important is that this quantity activity, number of disintegrations per second, actually okay, now we come to number of disintegrations per second is called becquerel, Becquerel. The short form is BQ. The number of disintegrations per second is called becquerel. And there is another unit called curie. 1 curie is 3.7 into 10 to the power 10 becquerel. So curie symbol is Ci, right? Capital C small I. So becquerel symbol is capital B small q. So disintegration per second is becquerel, but another unit is curie, 3.7 10 to the power 10 becquerel. Okay, now the thing is that we can capitalize on nuclear energy. We can capitalize on nuclear energy by way of nuclear reactor. So that is one way of harnessing nuclear energy. So to harness nuclear energy, well, there are basically two types of ways in which nuclear energy is produced in a huge quantity. One is nuclear fission. Fission is very heavy nucleus will disintegrate to give lighter nuclei. The other is the total opposite of that, that is fusion. That means very light nuclei will fuse together to give a heavier nucleus. Now in nuclear fission, if you take a very heavy nucleus like uranium-236, now you will have to bombard this with slow moving neutrons. If the neutrons are moving very quickly, then they may not be able to bombard the uranium at all. So you will have to bombard uranium with slow moving neutrons. If you do that, the uranium will disintegrate to give lighter nuclei. So for example, uranium-236 is giving this is actually giving iodine and yttrium, or it can give barium and krypton. So there are many combinations possible. This is not the only pair of combinations. There are many combinations possible. So, and then some more neutrons will come out as a result of the disintegration. So the concept is that uranium
53.
So the concept is that uranium will be bombarded by slow moving neutrons. After it is bombarded, it will disintegrate to give lighter nuclei, which could be any combination of nuclei, and it will give some more neutrons. But these neutrons, due to the concept of Q value which you have seen, these neutrons will come out with a very high energy. So these neutrons, if you want to recycle them, it's a big issue because they come out with a very high velocity. So you have to slow them down. So what we do is we use a moderator. So these are the uranium rods. So this packing is moderator. Moderator is usually heavy water or graphite. Heavy water is D2O, graphite, so you know. So heavy water and graphite, their job is to moderate the speed of the outcoming neutrons. These neutrons are coming out with a very high velocity. So moderator will moderate the speed and make it slow. So those neutrons which come out, their speed will become slow by the moderator. After their speed becomes slow, then they will be capable of continuing the reaction further. And meanwhile, there is a issue of chain reaction because it seems that it will never stop. So there must be some mechanism to make it stop. So you have a thing called control rod. Control rod is made of cadmium and it is a very good neutron absorber. So control rod is like a switch on and a switch off. Yeah. So control rod is like a switch on and a switch off. So if you fully insert the control rod inside the reactor, then the reactor will be completely shut down. It will absorb all the neutrons. The reactor will be fully shut down. And if you fully take out the control rods, then the reactor will be fully activated. So you have to basically use a pump mechanism to pump in cold water. So the cold water will come, a huge amount of heat is going to be absorbed by the cold water. It will become absolutely boiling hot water. That boiling hot water will come out, there will be a chamber, again there will be a transaction, there is another pump over here which is bringing water. This water will get converted to steam. Steam will go and rotate the turbine, and that turbine will finally cause electromagnetic induction, and you will have generator over here to generate the electricity, right? So that is the mechanism of a nuclear reactor. Okay, so what are the important components in a nuclear reactor? First of all is the fissile material, the material which is undergoing fission. So typically that is uranium. Secondly, moderator is heavy water, D2O or graphite. So the job of that is to moderate the speed of the neutron which is coming out. Otherwise the neutron which is coming out will come out with such a high velocity you will not be able to control it, and if it is not controllable, then the fission will stop. The fission has to continue. However, at some point of time you may want to shut down the reactor. So if you want to do that, there must be some control rods made of cadmium. If you push them right inside, the reactor will be completely shut down. If you pull them right out, then the reactor will be activated. And the other thing is that basically the fission itself can be of many types. There is no way to predict which one will actually happen, right? So uranium may give lighter nuclei like this combination or this combination, but the fact remains that it will always give fast moving neutrons which are slowed down by the moderator. So this is regarding nuclear fission. Okay, we are slightly hard pressed for time today. So nuclear fusion, we'll have to do it the next day. And the other thing is that I remembered that Fraunhofer diffraction, which we were supposed to do in wave optics, that we have not done. So I think Fraunhofer diffraction, nuclear fusion, and I think there's another topic, resolving power of optical instruments, that also we have not done. So resolving power of optical instrument, Fraunhofer diffraction, nuclear fusion. So all these topics I intend to do them the next day because these we have not done. So that is going to be the strategy for the next session. So I think maybe by next class or the class after that, I think we can say that we would have completed the syllabus to a fair extent. Okay. So today we are a bit hard pressed for time, nuclear fusion, and whatever topics are left, we will finish it in the next couple of meetings. Next couple of meetings definitely we'll finish everything. So that will be all for today. So I'll conclude the meeting and I'll end it now. Thanks a lot. Bye.